Today's lecture, we're going to talk about OpenCV and the skimages. And mostly we'll talk about the related tools that you can use for computer vision. Although we do a lot of deep learning in recent years, um, a lot of work can be replaced. A lot of tools that is traditionally used in computer vision can be replaced by deep learning models like segmentation, object detection, maybe like classifications, or maybe like image generations. However, there are still a lot of different tools, classical tools that can be still very useful and handy that exist in OpenCV and the skimages. Even if you are doing deep learning, like when you're doing a pre-processing or to analyze the problem involving with images and videos, there are still a lot of good tools that you can use. And besides, they still serve as great tools for building up a baseline so that you can compare your results in deep learning models with some baseline. A lot of times, if you didn't train your deep learning models right, and or maybe you didn't use your deep learning models correctly, you will get something seems to be reasonable. But if you are familiar with classical computer vision tools, you will see that even with some simple ideas and simple tools, you can get even better results. Our class repo is at this GitHub repos. You can visit with this link. This is not in our course repos, but for these lectures, I have an independent repo for all the results, at least most of the results and most of the code that use and demonstrate in these slides. So you can see it right here. It also included some more GP notebook that is not included in the slides, and there's also old slides about some fundamental tools and ideas in computer vision. There are many different approach that we can begin or study with computer visions. But in this lecture and the repo, the computer vision workshop is more towards the practical side. We are introduced, like the tunes in our this course, the data science software. We are most focusing on software and begin with the tools we will have in our hand, in our toolbox, and explain some theories or algorithm behind it. So let's begin with some history. So at the very beginning of the computer vision, it is usually contribute to a summer homework set from 1960s. It usually says that okay, a professor consider a computer vision is sort of easy. We can say that he underestimate the difficulty of computer vision. So he give some more assignment, assignment for some vacation, like doing a project to ask students to write a program that can do sort of computer vision things. But certainly, it was underestimated. The difficulty of computer vision task is underestimated. But if you go back and think about it, you may understand why they make such sort of mistake to underestimate the difficulty of computer vision, because back to 1960s, it already achieved some amazing result in the field of computer vision by using simple algorithm. For one thing, there's a famous demo called the blocks word. You can see that people put several blocks, like simple geometric blocks, like this one triangle, or some cube, and they write some program to do certain tasks, like move by describing the thing, or doing certain thing. The method they use is to use mathematical formulas and algorithm, like edge detection. For one thing, they use edge detections. You can see that because they are so simple, so they can use edge detections to detect the edge of things, and they use these informations. They compute the shape of this and use some algorithm to classify the shape of this geometric object, and they can do certain things. And they are sort of successful in this simulated world. So by knowing that they can successfully doing these simple toy examples, they gain some confidence that, okay, if we write the program more complicated and more carefully, maybe we can deal a more complicated scenarios other than this simple world. However, the achievement beyond this toy example or toy word, simple simulated word, is limited, because when we wish to apply this algorithm beyond the simple cases, the complexity grows up unexpectedly. Okay, but people still doing computer vision and studied and research, gain a lot of fruitful results. So in 1970s, even in 1970s, people can do something like optical flow. We will see it a bit later. This can be used to track object in a video and like estimate the movement of things, sort of all these things, and maybe useful for 3D construction, to reconstruction the 3D things from 2D images. So it already has optical flow since 1970s. And also there's a lot of like mathematical formulas to do like edge detection, even with more complicated real world images. So even in 1970s, they have already developed certain advanced formulas related to computer vision. In 1980s and 1990s, and even in early 2000, the computer vision keep growing fast and developing a lot of different algorithms. A lot of works that you can find them in the libraries like OpenCV or skimage. There are other libraries, including SimpleCV, dlib, and Cornea that we introduced in the PyTorch ecosystems. So let's see certain typical tasks that in computer vision, in the field of computer vision. One is super resolution. So this is a classical example of the classical example image of super resolution. So on the left side, it is an image that with more blur and low resolution. And people try to use some algorithm to make it more sharp or more clear. A lot of work has done in early 2000s, maybe not early, that just 2000s, can achieve pretty good results in single image super resolution. Although the more classical study field in super resolution, maybe like a multi-frame super resolution, or maybe in 90s or 80s, or maybe in 70s. I'm not that familiar, but at least in 2000s or 90s, a lot of mathematical formulas that you can, I think it's not that difficult. So a lot of theory may be already established in 80s. So the thing is that, so when we get just single frame of a video, a single frame from of an images, maybe we can only get some low resolution blur samples. However, if we are taking the frames from a video, because each frames can be considered as a statistical probability sampling, so we can, if we have multi-frame samples, because we can assume that the object doesn't move that fast. So if that assumption is true, then it becomes a mathematical problem, because we are sampling things. Although each sample is sort of low resolution, but because we are sampling multiple times, we can use the information layer exists in the video and reconstruct a higher resolution images based on the mathematical formula. A lot of new ideas comes, and so people, after the multi-frame super resolution has been matured, or a lot of theory has already developed, people are interested in single image super resolution. So a lot of creative ideas and algorithm has developed for single image super resolution. Like, just for example, that you can see what kind of ideas that can you use for super resolution, instead of using like mathematical formulas for multiple frame, because we only have single frame, single image. The thing is that even though we only got the low resolution informations at here, but because a lot of patterns repeat in a single image, so although we only got low resolution information right here, but we can use other part of the images to enhance our resolution, because we can assume that this pattern right here is similar to other places. Also, you might want to, like, for example, the two eyes might be similar. So that is some information that you can use. Besides that, you can also assume the images to be more smooth, or like if you have some certain assumptions, you can reconstruct image based on these assumptions. So there are many different ideas to do single image super resolution. However, of course, you know that after like 2010s or in recent years, the generative model, visual generative model has developed rapidly. So by using deep learning to do super resolution has become overwhelming and become an overwhelming idea and very effective. So recently, if you are trying to do the super resolution, you probably will go to search some kind of deep learning approach by using certain model. Even like 10 years ago, if we want to do the fast super resolution, we probably will do something like SR or I forgot the name, but like SRCNN, things like that. You train it like a super fast training using machine learning and by giving a lot of data set and you train a model to do the super resolution. That's probably the most typical way and maybe the easy way to do that in recent years by most data driven, not the idea or mathematical driven. But still, certain ideas, certain classical ideas can help you to improve your models in some sense. Okay, another typical, another task in computer vision is image completion. Maybe like if you want to remove or replace the background or remove some object or certain thing like inpainting. A lot of algorithms have developed for inpainting. So here is one example of using the inpainting technique for image completion. This is done using OpenCV. This is one of the OpenCV example. So you can see that even without deep learning, we can achieve the result like this one. So a true story is that when I ask people to do image inpainting, and if they are not using like just we said, these techniques will in recent years we probably will use some deep learning models, some deep models to do so. But if you didn't use the model correctly, or you choose the wrong model, it will do the inpainting poorly. But if you know what a simple algorithm can do, like this one. If this is something like a grid, like what we see here, and if you have already seen OpenCV example by using certain algorithm, then you know this sort of thing is achievable and it's not difficult. And this result is not difficult because the thing that need to be inpainted is sort of thin or not just a blob of a big block. If you want to remove object, that's a different story because that is sort of difficult. But if the object you wish to remove is so thin or so small, even though if you wish to remove a lot of different objects, but if each of the object is small, then by using certain algorithm, you can achieve some acceptable result. So by acceptable, I mean things like what you see on the right hand side. So this sort of result is doable even with certain techniques from algorithm from maybe 20 years ago. You can achieve things like this one. And in fact, deep learning can do better. So if you are using a deep learning model and achieve things even worse than this one, like you can see there are visible artifact or visible, like you get the red things right here and there, and it doesn't look like a bird, even if you even if you take off the glasses or you look it far away, then it is not acceptable. Okay, so even with so what I'm saying is that having some knowledge of what the classical algorithm can do is an advantage and can help you to use tools. Okay, so let's go to the tutorial that we have in the workshop. So the first one is I call it a tutorial classics, which includes a lot of fundamental and basic things in the computer vision. Not everything, but a lot of things. You can find it here. It's called exactly the tutorial classic, tutorial classic IPYMB. So you can find the. Let me open the notebook right here. It takes a while because there are a lot of images in this Jupyter notebook, so it takes a while to load the notebook, to render the notebook. But you can, if you clone it, okay, if you clone it, I actually modified it into English, but I haven't pushed it. I'll push it probably right now. Let me do it to push it to the repo. But originally it is a Chinese version. So if you are more familiar in Chinese, you can read the original one to get the. I also have a different branches, but the master branch is the latest one. I'm going to submit my. I will do it later because I probably haven't committed yet. But the things that you will see in my what I'm going to show you in these lectures is going to be in the English version, the latest version. Okay, so let's first go a quick look. We will discuss it most in the notebook form. But first, let's give a quick look of what it has. First, we'll read images and we'll see the, just like we do. Although OpenCV provides some functionality, it provides perfect functionality to read images. But like I probably have said before, I'm more familiar and feel more comfortable by loading images into using Pillow. That's what I'm more comfortable with and used to. This may not be a best approach because if you are using OpenCV, then probably you should use OpenCV to load the images, especially the channel, the color space used by OpenCV is usually BGR, not RGB. RGB by RGB we mean the red first. So let me first to load the code first. Okay. Tutorial classics. Okay. The reason that why I have to use the notebook itself, not the slides, will become clearly very shortly. Okay, but before I go into the notebook, let's first see how I do the image loading. So when we use the Pillow to load the image, it is going to be in the Pillow format. It can be demonstrated or rendering directly in the notebook if it was in the Pillow format, if it is in the Pillow format. So that's probably the reasons that I'm using Pillow more frequently, because everything is more expectable. However, in OpenCV, especially in NumPy, in NumPy, everything has to be converted into another format. That is in NumPy format. If you are working with OpenCV Python, image has to be converted into NumPy array. But as we can see, when we do the NumPy tutorial, NumPy lecture, we have already convert the images into NumPy array frequently. So that won't be an issue. However, one issue is that in OpenCV, every image is default in BGR order. The channels is start with blue, then green, then red. So here is a demonstration of by splitting one image one color images into different channels, but I don't think I need to explain it too much. But this animation gives a pretty good idea of how we represent color images in different channels. Because because of the biology things, how the eyes works, we usually split the image into 3 different channels. The most popular one might be the RGB, red, green, blue. There are something like YUV or like the lab color space, which we will show it a little bit later. In the printing, you probably will use some like CYMK or things like that. And some people is said to can sense more than 3 colors channels, like super color vision. Some people have some super color visions, but in general, we assume people, and of course, some people are more has sort of certain level of color blindness, or certain disability can sense less than 3 channel of colors. But usually, the image is represented in 3 channel of colors. Even sometimes it has a 4th channel, but the 4th channel is the alpha channel, which represents the opacity of the pixel, not related to color, but related to the opacity. So this here is a simple example that we split the images into 3 different channels. So each channel contains red, green, and blue. In the notebook, we are using NumPy to do so. So let's go to the notebook and to run the code. Okay. So you see that I have translated the notebooks into English already. So let's first read the image, and then we see the shape of it is what we do in NumPy, and we can check the first. This is the second one, so it is a green channel, and because we times it with kind of masking it, so we are using a NumPy operation to make it everything becomes little except the second channel, which is right here, indexed right here. So it will become a green image. If we keep the first 2 channel, it is R and G. So here's blue. Here is R and G. So you can see things like this one. This looks like an early color movie. There are some technologies called the tech color, because original the movie doesn't have 3 channels. It only has 2 channels. The 2 channels is more like red and green. So they lack the color of blue. Not exactly the. I think it's probably not exactly the RGB that we are having in the modern specs, but it is more towards the red channel and green channel. So the early movies, early color movies, will look a little bit strange because they have some funny colors. The reason is because they didn't use the full 3 channel. They are using 2 channels, and these 2 channels are more like a red and the green ones. So if we only let the green and the red pass through and discard the blue channel, it will look kind of like the old movie. If let's compare to the original one. The original one is more looked like like what we see in real life. But if we discard the blue channel, it still looks kind of like a color image, but you just cannot tell it looks kind of funny. The reason is it only has 2 channels, not 3 channels. But let's keep it to the original meaning, because I call it IMG, which I keep only green channel. And this one I only keep a blue channel, a green channel, and the red channel, and combine it to make it more visually pleasant to see. Okay, we can split the image into 3 channels. Because the original workshop is very fundamental and for beginners, so I'd explain it in more details, but I don't think I have to explain it to detail right here. However, like what we do in the NumPy lectures, one of the operations is to do blur, to make the image to be more blur. So here is a functionality which we call the Gaussian blur. What is blur? Blur is sort of doing things like considering the average or like the mean of this pixel around its neighborhood. So there are different definitions of the average around this pixel. Like you can take a median and for a certain region. So region can be small or big or large. Or you can take a mean. But this mean can be weighted mean. Or not just the uniform mean in a window. It could be something like weighted mean centered at this pixel. So if we are using a Gaussian distribution, like functions, then it will call it like a Gaussian blur. Because for the Gaussian functions, the Gaussian distributions, you can have certain adjustable parameters. Also, we can if we are increasing this x and y, you can see it getting more blur. And if we make it smaller, like in x direction, it will sort of like a motion blur. If we do it in a different way, like pretty large x and small y, it will look like a motion blur in the horizontal direction. What we do the opposite is kind of like a motion blur, but in the vertical direction. We can choose them to be both small. And okay, then it will become more smooth, but a little bit blur, but it's not such dramatic changes like the feeling that we get a pretty large x and y. Also, here's a function, the CV Gaussian blur, and you put an image here and get the x window size, y window size, and it will compute the other parameter automatically, and you can get things. So here's a interactive demos that you can work with this notebook. So here, this is the major reason, the primary reason that I am working on notebooks, because I have to work it more like in an interactive way, which I cannot do it with slides. But why do we want to blur a image if this image is pretty already good? I mean, the image that we already have is perfectly fine. It's just totally fine. Why in the earth we need to blur it? The reason is, there are many different reasons, but the reason is the most picture we get will have some level of noise. More or less, they will have certain level of noise. So if we want to do more further operations, you probably want to denoise it. And one way to denoise it is to blur it. To blur it. So blur is can do the denoising. So a lot of time we want to blur it before we do other operations like edge detections or other certain operations. So that's a usual technique we use. And another primary use of blur is we can get the information from surrounding pixels to these pixels, like the local mean of image of this pixel. So we can compare this image. Compare the color in this pixel with the surrounding average or mean with the color of this pixel. So that may be useful. So that's the two primary use of using blur. There are many different other usage, but this is one thing that is pretty useful in your toolbox. To illustrate the noise of this image, let's add some manually add some noise into these images. So I add some image noise into the original images. I'm not sure you can see it, but I can see it pretty well. Maybe I can use this one to do that, to make it into a more high resolution. So you can see that in this one, if we make it small, we can still see what the flower, and probably we can still pretty sure the boundary of this flower. But this images is getting quite noisy. Just recall the black world, what we mentioned in 1960s. There's a black world. One of the difficulty of computer vision is that in real world, the image is getting more complicated and probably more noisy. So if we want to do the image processing in real world, we have to deal with the noise. We cannot expect our image to be perfect. Probably in last lectures, when we discuss homework, we see the Pikachu's images. It looks like it only has 4 different colors, like yellow, black, red, or white things. But in fact, if you really look into the values of the each pixels, you will see that there are different white in the white color because there are small differences, and there are different black, different yellow, and different red inside it. It not only has 4 colors, it has a lot of different colors. So before we wish to do the homework things, we need to we first do the clustering to reduce the color first. So this happens a lot, even though if we are very easy to perceive these images and can recognize it as a flower, and we can pretty much show what the boundary it is, but it is sort of difficult for computer vision to do that if you are using some algorithm to do so. So we manually add some noise to illustrate the difficulty. So let's do some blur to see whether if the things get better. So right now, if like you can see right here, the noise has getting it's disappeared in here. Although it get more it is less clear, less sharp, but we can but at least we can see that the color right here, is more smooth and have roughly the same color. But in the noise images, it is very kind of difficult to see the boundary if you really think about in algorithm, because our eyes are pretty good to identify and to do the visual task. So it is easy for us to identify, okay, this one is the one block and this one is another region. But if you really look into the pixels, the colors are kind of jumping up and down. So if you want to write an algorithm, it's pretty difficult to do so. After we do the blur things, we can adjust the blurriness to see, because if we sort of reduce the blurriness, you can already see some noise here. So here is something you need to find the middle point to balance the noisiness or blurriness. You can, of course, make it very, very blur. Depending on your task. If one only want to see the difference of the regions, it probably, in this case, using a lot of blurriness is probably still okay. But in some other cases, you want to have more details in the boundary, then you probably should want to have a less blur image to make a more detailed in boundary of the edge of this flower. Okay, so let's try some simple example. Here is a simple example. We want to simply use a threshold to find the red flowers. So my algorithm is pretty simple. That is, I'm using, okay, first I'm using a blur, but I'm not using Gaussian blur. I'm using medium blur. Instead. You can use a Gaussian as well, but in this example, I return it to the medium blur. It is probably that I modified in the workshop lively, because maybe I change it from Gaussian blur to medium blur. But in the current state, it is, I'm using medium blur right here. The Gaussian blur should work just as well if you are choosing correct parameters. So if you're interested in the historical version, you probably can check the other branch for the early version. So I'm introducing another way to do a blur using the median blur. So it uses the median instead of a weighted mean using Gaussian kernel. The task is simple. We use the mask here. The mask is that the red channel is greater than the value of the red channel is greater than the blue channel and the green channel. So the red color is a dominant color. That's the simple filter. So because it has 3 components. So suppose the red component has the highest value than the second one, like the green one and the blue one, then we choose that pixel. So if we do so, this is the result. We get of course we get a pretty good boundary of the flowers. But if we didn't do the blurry, we simply do it with to the original image, then we get something like this one. It still looks pretty good, but if what we want to do is to find a region, because the difference of the color is just for visualization. Imagine that we want to get some connected component regions in this graph that is more red than other colors. That you can see that this boundary is is better. If you are not doing the blur, what you are getting here is something like this one. You are not getting a very clear, simple regions. Although we still get some small fractions right here, here, and here. But compared to this, the above one is much better. Also, here is just a simple illustration of why we need to blur a seemingly perfect fine image. It's because it will help us the other operations that we apply on this image to be more robust. That's the one of the region. Here is another demonstration for the medium blur. Okay, so we change a different size. The median is more sort of more robust to certain. It will get more sharp boundary than the Gaussian blur. You can see that although the color seems to be a little bit funny, but you can see at least it has a pretty sharp edge on the flower. And already the color right here seems to be already quite noiseless. Let me put it more, zooming into more. You can see that it already like black, the white flower, red flower, pink flower. It already become more like one color. But still we got pretty sharp boundaries compared to the like here. It is more blur. It has a more blur boundary. The boundary here is more like more sharp. You can try it on the notebook if you cannot see it quite clearly on the streaming, but you can see the differences. There are other more advanced methods to sort of like preserve the sharp edge and do the filtering. So one way to do that is to use the bilateral filtering. It uses certain mathematical formulas like this one to sort of estimate the edge. The edge of the brightness or the colorness. So if it detects something like change rapidly, it will keep it. But if it detect something like there's no different trend around it, it will make it more smooth. The idea is that what I was saying, but you have of course you need to do something to translate that intuition into a mathematical formula, and it always involves some trial and error. But this here is a formula, and you can use that. It also has some adjustable parameters, but you can see that when we apply to our noise images, it will keep the clear boundary here, and still the noise seems to be reduced, and we didn't see much noise on the white flowers or like pink flowers. So let me run it. Okay, I think I run it already. And you can adjust different parameters to see what will. Of course, if you put the sigma color, sigma space to be higher, it will become more blur eventually. But even with such blurriness, we can still see the clear boundary between the white flower and the background. Let me put it in the 4 parameters, in the largest one possible in this interactive demo. You can see that still has a pretty clear edge in the boundary, even though each flower has become more very visibly blurred. So we probably want to reduce the parameters as long as the noise is less visible and maybe more acceptable. so we can get a quite clear image. So this serves as a noise reduction algorithm. Can be served as a noise reduction algorithm. However, for the noise reduction task, there are many algorithms is used for dedicated for this task. Like here's one, the fast NL means maybe the non-local means or for denoising. So this algorithm is specifically for denoising. Again, like other classical method, you have a lot of parameters you can adjust. This is a typical characteristic of the classical computer vision utilities. You usually get a lot of parameters to tune because these algorithms are usually working, but the parameters has to be tuned before you can apply to your task. So sometimes you are using these OpenCV tools. You think, okay, this doesn't work quite well. The reason is you almost always have to tune the parameters. You don't use the parameters in a demo. You have to change the parameter for your specific task. So each task requires a different parameter. So usually the algorithm work, but it doesn't work out of the box. You have to do some adjustment, do some settings before it can actually apply to your image or your task. So that's the mindset of using utilities in OpenCV and the scikit images. You always has to change the parameters, and also like we just demonstrated, usually algorithm has to work with each other. Like you have to blur or convert, do some pre-processing before the major algorithm to work. Also, like here, we usually do some blurring before other tasks. Also, that's the mindset of using these tools. Kind of different. If you are used to the deep learning models that usually works like end to end, or it already has a pipeline. So everything it has to learn to adjust is already adjusted by using the machine learning algorithms, by using the training. But for computer vision functions, you have to adjust the parameters and maybe combine several different tools together. Okay, so another very popular and frequently used pre-processing algorithm is to change the image into grayscale. Like here, here's one formula that is very popular to change RGB images into grayscale. We times R by 0.299, and the green channel times 0.587, and the blue channel times 0.114. Or not just simply average everything. We have to do certain weighted average of these three channels. There are different formulas for different systems. So there's no one formulas for every system. This is definable because there's no one standard, one natural standard like the gravity constant or like the light speed. There's no constant for that because these three channels is based on the biology, but the biology of different people has slightly different. So there's no one standard for everything. But this parameter is pretty popular one. So there are different standards, but this one is one of them. And you can check something like NTSC, that is a TV signal, because television is so popular. Also, like PAL, PAL, and NTSC are two major the protocol for radio transmitted television signal. So their color like the standard is pretty widely used. So anyway, we can use the OpenCV to convert the color from one images to another. So here use the typical RGB to gray. So because right now we are using the color images like JPEG or PNG, the correct way to convert this color is using the like the color standard in JPEG or maybe in PNG or the image format. So in computer image, or let we say in computer image, so we're using the standard here to convert the color images into gray image right here. So one popular application for algorithm as edge detection, and a lot of edge detection works only on grayscale images. So here's one way to do that. We're using Laplacian. The good thing about the benefit of using grayscale image is that it only has one value instead of three, because it only has one channel. And the reason that we convert it to grayscale before we do the edge detection is that we can still find the edge even within the grayscale images. So if we can see the boundaries in the grayscale images, then it probably should be fine. And working on grayscale image is easier. Okay, so one way to do that is using Laplacian. So you can see this is the result of Laplacian. And get a lot of different edges. At least it is certain edges of the images. Let's apply it to the SODOC 数读 the image of it. So here we load a simple SODOC image right here. What we are trying to do is to find the edge of this image. Okay, so you can see that by applying Laplacian on the above image, we can get the following. And we can imagine that we can do further things like OCR or like parsing by using the information, the edge information we get right here. But before that, let's do some visualization. We combine this image together, kind of making it like an overlay onto the original image. It is not very clear, but I'm trying to make some green lines on it. Or maybe I can reduce this color like you can see it more clearly. Let me rerun it because I have to. Okay, you can see that it may make it more clear. We apply it on the original image and get some overlays information on these images. Another way to do the edge detection is to using Sobel, like Sobel X and Sobel Y. As the name suggests, they are using mathematical formulas, and in fact, they are using the tools that you studied in calculus. That is the differentiation. So Sobel X and Sobel Y is basically the partial derivative of x-axis and y-axis. But because we are working on a discrete space that we working mostly on numerically. So everything that originally from the calculus can be implemented in like a convolutional kernel, because every derivative with differentiations, we are practically using numerical differentiations. So these numerical differentiations, no matter it is x-axis and the y-axis, they are sort of like just doing the convolution filtering. If you check the document of the computer, like OpenCV, you can see it will show you the kernel of these operations, but they are all implemented in like a convolutional filtering. So here is an example result of the SODOC image. You can see that one direction find the x direction find the difference between along x-axis, so it get all vertical boundaries, and the Sobel y found the horizontal boundaries very clearly. A popular way to do edge detection is scanning. Although Laplacian and Sobel is more close to the original concept of differentiations, but in order to do proper edge detection, it still needs some work to kind of merge and integrate all the information you get from the derivatives. So scanning is one popular way to sort of merge and integrate all the differentiation informations to form the task of edge detection. So here's the result on the SODOC. As you can see, it gets more clear result comparing to the Laplacian or Sobel X and the Sobel Y. So for one thing, Sobel X and Sobel Y only works on one direction. Sobel X mostly was on the x-axis and the Sobel Y is on the y-axis. And Laplacian works on all directions, but it is not optimized for edge detection. So although overall it seems very promising, it's still not quite there. And can it do the details? So it is focusing on edge detection. So the result we get is more like what we are expecting from edge detection. Of course, you can apply like the blur or like bilateral or other filtering to denoise, and you might get better results. You can try to combine all the things we did before to see what it happens. But let's first see it applied to playing cards. So here we load both of these images, like the SODOC and this is just my randomly pick example for doing computer vision. This is not an example from the OpenCV official website. This is just a simple image that I take by my phone or my camera. I forget, but I think it might be from the phone because it has been already a while. But the way that I take these images is because I know these things should work for OpenCV functionalities. So for this one, this is for the I just pick a few different cards, playing cards, and put it, spread it on it is actually a sofa, on a sofa. It's not on a desk. By applying edge detections, this is something that we get. We don't get the edge of the S card and the Ace of Spades and the Two of Diamonds because they are both more like white things. By carefully adjust, you might get this edge, but you might get some unwanted edges. So here is the parameter I tuned so that you can get pretty good images. At least this is what I think is the better result among all others. Again, I overlay the edge detection result on the original images to get some visualization so that you can see. Okay, so you can imagine that we are working on like AR augmented reality glasses, and this is something that help you to do the visualization. Also, here's the result. We overlay the edge detection result on the original image. We can use other algorithm combined with the edge detection. One of them is the hue line detection. Hue is the name of a scientist. He invents certain formulas to make some algorithm to do faster. That is the hue transformation, which is a very interesting technique. That is one of the interesting technique. A lot of technique is not interesting, but hue transformation is one of the interesting technique, which is unfortunately we are not going to talk in details about it. But it can be used for line detection and circle detection. If you don't use it, you can still use some brute force to do that. Pure brute force to do that. But it requires more computational power. So usually we just use a hue line detection. So by using hue line detection, we are trying to find the straight line segments from the edge detection results. Because the card is quite like a regular angle, so we are expecting it to find a straight line like right here, here, here. And in fact, it does find a lot of different boundaries straight for this playing card. I would say it almost perfectly. Maybe I can tune down a little bit about the requirement of the length of the straight line. So maybe I can also detect this one. Let me check the original one. Yeah, because we have this one. So if I adjust the threshold of the minima length like here, let me try to do, can we do a more dramatic change? No, we didn't find it. Minima length. Okay. Maxima. Okay, this may not be. Okay, we got listen. So by adjusting some parameters, we can have the whole thing. But probably the original one is better because I have already tuned it a little bit. Okay, maybe not. So you can still adjust it. No, maybe this one is good enough. Okay, that might be too large. Okay, so this one we get more full boundaries, but we get some false positives also. So you can adjust the parameters to get different results. But basically, it can help you to find all most of the boundaries quite easily. We can also apply it to the Sodok example. Right here, we actually got the grid pretty good. We can reduce the max line gaps to make it more clearly, but you will see that it will have more gaps right here. But if we put it into the original one, we get more straight line. There are more adjustable parameters you can check in the menu. Like because these two these two straight lines are too close to each other. Maybe we should just choose one. The longest one. Maybe there are some adjustment that you can apply on this transformation. You can check the manual, or you can do the post-processing to filter out all the result that we get from the line detection, and filtering out the unwanted things. But from the result we get so far, we can already, because we know it as like a Greek, like a chessboard like structure. So from the things we got here, we already got the straight line and enough straight lines we need, and we can already by using some algorithm to find out the actually the grid size of this sort of let's say the board, the chessboard pattern, or we can find everything. I haven't implemented the algorithm yet, but this is quite doable and sort of robust. Another thing is to find the corner, because sometimes not only we want to find the straight line, a lot of time we only want to find the key point. We want to find the key point. So one of the key points is the corner, because you can see that here is a corner, here is a key point. And we do not use the hue line to do the pre-processing. We can find, there are certain algorithms to find the key point directly. So one way is to use the corner Harris. It is sort of like a object detection thing, but it detects the interesting point in this picture. And by interesting pictures, it is define the corner of things in certain sense. So here, we are plotting each of the key points. You can see that here is a corner because here is an intersection between two flower leaves here, and here are some points of the flower. So you can see it does find out certain interesting points. So what we can do with these key points, one thing is that we can track the image, like in a video. If we put the point out all the key point, suppose the key point is a corner, it will remain to be a corner in different image frame, so we can track these things. It's sort of like the optical flow that we were saying, and it might be one way to do to implement the optical flow things. But here, we are using a more advanced key point detection. A more advanced key point detection method that we call the SIFT, S-I-F-T. The SIFT is one of the go-to key point detection method that if you are working with the OpenCV library or other library, if you are using a classical computation method, it is one of the most advanced one. I think it used to have some patent things around it. You have to pay money if you want to use it commercially. So sometimes people doesn't really like SIFT, but I think SIFT is pretty robust and quite useful. It can serve as a pretty good baseline if you are trying to develop some new algorithm for key point detection. There are other alternatives, but SIFT, in my experience, SIFT is one of the best one, and probably I would just use it. But there are some new techniques like using deep learning they can achieve pretty good result, like super points that is used in super glue algorithm. So now probably I will use super glue if I want to do the key point detections, but safety is still pretty good. One of the major problem safety solving is that the rotation. So if a corner is rotated, it is still a corner, but they may look, if after we detect each key point, we are associate each key point with some features. Then we are trying to match. If we have two different frames or two different images, we'll try to match them. And the Shift provided a rotation invariant features on these key points. Let me first to run it so that you can have an idea what I'm talking about. So here's a simple interactive demos. In these selections, simple option menu, I can select different card right here. And it will compute on fly. So what does it compute? It will compute the key point on these small template images. And it will also compute the key point on these original cards, playing cards on sofa image. And because it find a lot of different key points, it will run an algorithm right here, to match the key points. And after it match the key points, it will find out, because if you have enough key points matched, like here, we can find a transformation from this playing card template to here, this one. So it will not only find the key point matching, it will using the matchings to find the transformation from this guy to this guy. So that's why I can find the boundary, because each of these template playing card images are taken by the cameras independently. So for each one, I'm mostly using a more flat or straight angle to the card. So it will in a rectangle shape. So I'm using this shape do the transformation and drawing the boundary of this image on here. So you can see here is a pretty good example, because although I'm trying to make it more plain or more straight, I still get some corners right here. And you can see it's because the mapping, there are two valid mapping, but it turns out it chooses the rotate one. So you can see that this guy and this guy are mapped. So it will have some corners right here. No, right here. It has some corners right here. Right here, and you probably cannot see here. So maybe I will move it up. So you will have some corner right here. Okay. So for example, for the other one, the axis, most features are mapped from the center one. It also has some wrongly matched one, but because the vast majority is mapped correctly, so it still get a pretty good transformation. The one that doesn't work well, this one still works pretty well, and although it matched few key points, but this one doesn't work very well, because in principle it cannot work that well, is because the pips, that is the ace and the heart, the smallest one, these two guys, they can match to each other. So you can see that this one already maps to this one maps to this one. It maps pretty good, but it sort of by chance. There's no reason to prevent this guy also match to this guy. Although you can do this more in algorithm, but we didn't deal with these things in our algorithm. So algorithm is going to be more complicated. You need to have a more global matchings target in order to optimize a more globally sound matching. The last one seems to be the most valuable one, because you can see that this one does not match correctly. Although the S1, it is getting lucky. So the upper pips maps to the upper one, the lower pips maps to the lower one. However, this one is not getting lucky. The top and the bottom pips are matching to the same one, because I'm doing this deliberately because I know the issues about this method, so I deliberately cover one of the pips. So I kind of forcing both of them map to this guy. So you can see that it doesn't have a green rectangle. It should have one, but probably around here. So it doesn't work correctly. The reason is that we are pushing the boundary too much, so it cannot match it. Even with some global algorithm, it probably doesn't match. It's probably difficult to match it in the right way. So anyway, you can see that it doesn't work on this example. And I deliberately constructing this example. Okay. So, but anyway, you can see that even without deep learning models, this already works kind of like a few shot object detection. Especially, let's not look up at the failed example. Let's look at the successful ones, or maybe like these ones. You can see it serves kind of like a object detection, and it works like the few shot object detection. So if this is your scenario, your task scenario, the classical method can work quite well on this scenario, but it also has some limitations. But if you really doesn't have many training data, this is probably the way that you can use. If you are working on object detection, a lot of people are asking you, because they are not familiar how it works. It will give you something like 10 sample or 20 sample training data. It is not work with object detection. It may works, but it only because you are getting lucky, or the problem, the task is you are trying to solve is too easy. If you only have like 30 images, you cannot even do the proper testing to verify that your training is working, let alone to do the training, because it's too less. Like what we mentioned in the guideline of scikit-learn, if you have less than 50 images, you probably should ask more samples. And the 50 sample rules is for like the task that typical for scikit-learn. And if you are doing the deep learning, it usually requires much more samples than the typical task for scikit-learn. So if you are facing some tasks that you can only get just a few examples, then probably you can use this thing as a baseline to see, okay, at least what we can do is by using this matching method, using the feature matching, and we can match the template. And if effectively practically this is a few shot object detection. Okay, so let's see the more examples. Okay, so here is I have more examples in the notebook. So one of them is the old photo restorations. So here is the final result, one of the final result. But I'm going to the notebook and to see the more detail. So old photos that is taken by actually physical cameras and has a film. Because of some chemical, the property of the chemicals on the film, some of the color is going to be degrade after time. So you will see that yellowish old photos. It depends on the chemical that used on the film. So we can actually do by using OpenCV to kind of reverse or restore the original color. That involves with some knowledge on the color space. Okay, so let's see the tutorial on auto photo. Probably I should make it larger. Auto photo right here. Okay, so the image is still available on my old blog. Let me read the image, original image. You can see that this one is the yellowish old photos. So definitely the color need to be aligned. So one of the way to do that is do the white balance in Photoshop. You can do it in using white balance. If you have a old photo and you want to restore into restore the color, so it's actually quite easy to do that in Photoshop, since basically what you do is to just do white balance. But how do we do it in OpenCV? So one way to do that is to do the equalize the histogram. So because we have three different channels, three different channels, and we know that the one of the channel is degrade, which means the color range or the strength of it is reduced. It probably reduced in certain ways that we don't know. Maybe we can, if we have more knowledge on the chemical behavior, then we can model it using more mathematical way. But we don't, and we probably don't want to do that. So one way to do that is simply to make this channel as effectively as possible. So one way to do that is to do the equal histogram. This way will extend the channel to make the distribution to be flat. Here is the result. The color is okay, but because the color degrade is not the only issue of the old photo. There are other issues like the noising. So although the color seems to be quite okay, but the image is going to get more noise because we effectively making the images to be more contrast. Because the old one, the color is degrade, we make it more contrast. So the noise is getting more noticeable here and there. But the color itself is getting back. We will deal with the noise later. So here is the original histogram of each channel, like blue channel, red channel, and the green channel. The green channel is more toward the higher range, it's getting more green, and the red and green red and blue channel is more concentrated on the lower side, and the highest part of the red and the blue is kind of limited. So by doing the equalized histogram, we are trying to make the histogram of each channel to be more flat as possible. Also, here is the result. Okay, so comparing to this one, we'll extend this to the all possible values and making it more flat instead of concentrate into just a single mode. However, like we find out the image is getting more noise. Luckily, we have already introduced and see certain method to do the denoising. So why not just using one of them? So I'm using the fast NL means denoising color, which I used in the previous example, and apply on these images. So here's the result that I get. It seems quite okay. It seems okay. However, so we can stop right here and say claim it a day, because it is what you can do. You can change the denoising method and probably do certain thing on the equalization, histogram equalization, instead of probably mix up the histogram equalization with the original. You can also extend the range directly without doing the equalization part to make it to stretch out the color range. That also works, but you are not getting much more. The reason is that the old photo is not using RGB color channels. They are probably using a different, because different color space, because there are different color space, like lab color or YOV color and or other colors. The old photo is mostly depends on the chemical it used. So there's no reason it will comply to the RGB standard of the computer vision. So maybe we can use other. We know that it is the degree part is one of the chemical, and because it becomes certain of yellowish, so probably the one of the channel might be the yellow channel or sort of a yellowish channel. So we may want to use other color space. There are different color space. So first one, we are using YUV. So we convert the BGR from BGR space to YUV. So let's see the different color space. So you can see here's YUV. YUV is another very common used color space. Y is standard for the brightness. Probably I should use the English one. Y is for the brightness, the luma component. Because as we see in the grayscale conversion things, we know that the brightness or the luminance is one of the key component of the image of visual cues. It also like biological based. The thing is that a lot of people have certain color perceptive related defectiveness or differences, but most of people can still work very well on the society and the real world. However, if you have the property of determine or kind of distinct between the can distinguish between the light and the dark part, then you will have trouble. Even though if you can tell the differences in color, but by removing the lightness, the luminous perception, you will have very difficult to do the works with visualization. So that's why we have a black white TV, but we don't have a color TV but without the brightness channel. So the white channel is definitely one of the principal component, although in different meanings. Like we we do the PCA, but colorness is probably one of the primary channel. So YOV, at least it makes the brightness into one of the channel, and the U and the V are independent, are other channels related to other things, and it also gamma corrected. Also, it has a nonlinearity between the RGB and the YOV. Today, like Wikipedia said, we're also using the YCBCR things as well. Okay, so let's try it on YOV color space. Here is the result. I'm pretty much doing the same thing, except I'm converting it first to the YOV space. And doing some operations, more operation right here, to kind of mix up with the original one and the corrected one. So you can see that it is denoised, and I cannot tell the much difference between this one and this one. I cannot tell which one is better. But by working on YOV, it can get this result. But another color space is probably need more attention and more sort of more nature to our eyes, to our perceptives. That is the lab color space, LAB color space. If you are working with some nature perception, lab color space, LAB, is more, it's probably one way that you can go and can work more naturally. It has 3 channels, L, A, and B. L is also the perception of lightness, about the brightness or lightness or luminous of like YOV, Y, and A, B are different colors, for colors. So although I didn't make sure the old film, like the color film, is related to lab color space, but because lab is more corresponded to, associated to our perception, also it seems to be good to try on the LAB space. So that's why the last example here is try it on the LAB space. Although the differences is not much, but I would say that LAB result is a little bit better than both the YOV and the RGB one. Also, that is my conclusion. But I mean, at least for this notebook. But the thing is that you need to I want you to understand or to realize that there are different color space. Sometimes if you are working on RGB and it doesn't work quite well, probably a more nature space to work with is probably the lab space or the maybe YOV space in some like if you're working with MPEG or like AVI, like video files, YOV is probably more common to use or natural to use, like a natural format or video. And if you are more like working on a task more related to the perceptual, human perceptual, then probably lab space is something better. So instead of, because we are mostly working on the equal histogram, so the choice of different channel is quite important. So that's why I am exploring the things with different color space. Okay, so let's continue to see the next. The next one is the perspective transformation. It's kind of like a rotation or kind of like the translation and movement of things, but it is in 3D space. So the result is what we were doing is I'm getting this guy into making it more flat like this guy, because we know it is a flat thing, a rectangle in 3D world. So, but we are getting the image to mapping to projecting the 3D world into a two-dimensional image. So it is not a triangle in the 2D space, two-dimensional space. However, by doing, because we get some information like the corner, we can do the transformation to figure out the transformation. Well, by assuming the camera is already calibrated. The camera is usually not calibrated, but by if the thing is nearing the center of the camera, and you don't see much like the warping around the images, then it probably, you can probably assume that the image near the sample is kind of already like the ideal model. So we can apply these things to compute everything mathematically and make it right. You can see this example in this notebook. The notebook is the perspective transformation. Okay. Although this one doesn't have much interactivity, but here is one of the example that you can see. This one is taken from, I think it's from a Creative Commons. Pixel. This is library, and this image is Creative Commons in Creative Commons license. But it has a billboard right here. So a billboard is a perfect target that we can apply our perspective transform on it. So maybe we can get information, because usually we have insanely high resolution on our the photos that were taken from our phone. So although if we transform back to a flat one, it might, a straight or flat one, it might lose some resolution, but because the original resolution is quite high, so we are probably still good if we transform it back to the regular angle one. So here is a transformation. And first, I do it manually to find out the four corner of this. We are assuming this is a recurrent angle. I can do it for like on the white, the billboard one, but because you can see that this guy they may have cut it a little bit, and you can see some curve right here. So instead of using this four corners, I'm using these four corners, or these four corners. Because this one is an image, I can make some assumption on the aspect ratio of it. I make some assumption on the aspect ratio of it. But anyway, I get these 4 points by simply I try to plot this polygon on these images and just try and error. You can get these 4 points. Or a better way to do that is open this image in the Photoshop or like a Paint. Move your cursor to the point near here. You will get the coordinate. And by plotting it on it, you can do some small adjustment. You don't have to have a perfect coordinate. But get it as accurate as possible. Okay, so after I get this coordinate, I do the transformation. And by calling CV get perspective transform, and do apply the warp perspective to apply transformation. And I'm assuming each corner maps to be like, I'm assuming the resolution, the perspective is like 1920 and 768. This requires some guessing and experiment, but I'm guessing the aspect ratio is sort of like this one. It only depends on the aspect ratio, the ratio between the W and the H. But anyway, this is my assumption, and all I need to do is tell that these 4 points, if I wish it to map to the 2D plane, I wish them to map to these 4 coordinate. And by applying this transformation, I'm applying converting everything to here. So this 4 corner, the 4 corner of this photo, or this formal photo of 2 people, this coordinate will map to the coordinate that I wish to have. Of course, because everything on this billboard is on the same plane. So assuming my guess of the perspective ratio, aspect ratio is correct, they will map correctly because they are on the same plane. And these windows on the building is not on the same plane, but they are parallel. So they are probably, and they are very close to these images, so they are probably just fine. They are just fine, because you can see that they are still in the right structureness. However, this building, you will see it will kind of warped, because originally you can kind of because they are not in the same plane, and they are not even parallel to this billboard. Also, the structure of it will getting incorrect and looks pretty funny. But the target we wish to have is this one. It's going to going to get the correct label that you are working with. So sometimes this is quite useful tools to, like, if you are getting the logo, but all you have is logo of some brand, but all you have is a photo that is kind of transformed in a perspective way to transform it. So you can transform it back to see the original image of the original structure of the logo, and by using it to apply it to other template matching or other use case. Here's another example, pretty much the same, but in this one we can see different object that we can apply our perspective transform, like this billboard, and this one, and this one, and this one, and this one. I probably have already tried it on this guy and this guy, because these two guys are already quite straight to us, kind of straight facing to us. So I tried on these two guys. Both of them works, but the example below is probably the 蒙甲鸡排, this one. So you can see that we can get the correct logo of this 蒙甲鸡排. And by using this example, you can see the blurriness of this one. That is because we get different resolutions, X and Y, because this guy has a little bit turned to this way. So you can see that the X resolution is getting squeezed. So if we make it flatten, it will kind of like doing it with some blurriness things. So then you can apply some like super resolution or things, other operations on these images to get a better result. Also, but this one is very useful to do the pre-processing. Okay, another example might be okay, this one. This is combined with the object detection. What I'm using right here in the notebook is using the eye detection and the face detection on the OpenCV. Maybe I'm showing it. Which one? Face strip? Okay, yeah, this one. But what I'm saying is that although your eye, in this case my eye, is not a plane, but because the edge detection, I mean the eye detection here using, I'm probably using DLib or OpenCV, I forget, but you are going to get a polygon of this eye. So you can see that we get a polygon of this here and the face shape. So although the eye is not on a plane, but I can kind of assume it is on the same plane, and I get probably 4 of the points, and comparing to the template, so I can do a transformation, perspective transformation, just like before. If I get 4 points, 4 or more points, so I can map manually. You can see that this one is doing manually here, and I got these coordinates, so I can map these coordinates to the detect coordinate, so I can stick my these images on the eyes in the correct position right here and here. Although they have different angles, different shape, different size, but by using the simple segmentation, object detection things, and by applying the perspective transformation, you can stick these things to the face, to the eyes, in a more seamless way to look more natural position. Of course, it is not nature, but it is more the location is kind of nature. Also, that's the way to use it. Also, here's the result to a different angle. You can apply it to, and you can actually see it is more quite fit to the actual eyes. Also, that's one application of the perspective transformation. Okay, another way to combine with the face detection is I'm using the face detection and using some simple algorithm, and by using the warp. But in this kind, we're still using a warp transformation, but we are using a more we're not using perspective transformation to map things 1-to-1, but we are trying to customize our transformation. So here is a single example that after I do the face detection, the head detection, I can use this information to control my own filter to enlarge the head. I'm not trying to hide the the transformation, because a lot of people doing you can see that this one is getting curved, because definitely we are doing something photoshopped. But I'm not trying to hide it, because definitely this is not nature. This is something modified. But by combining simple algorithm with the information we get from the computer vision things, we can do some more creative things. Like this one might be the remap things. Let me see. Okay, this one, tutorial remap. I'm applying it on different images. So at the beginning, we are working on the flower images and contrasting certain to showing that you can have many freedom to warp or to transform the images, even in this way, like a sine wave. You just translate one coordinate system to another. You simply give it a map, and it can do that. Then we apply this to these images, and we detect. First, we detect the faces. Of course, this one you can replace it with other method. There are a lot of face detection deep learning models works better. But again, this one shows that even with the OpenCV, more classical ways to do that, this is achievable. So we're expecting the deep learning model to do even better. But anyway, it detects this head. And by customize some algorithm, I can make them to looks like have a bigger head. So here's just some example, and this might be I using different parameter or different way to do the warp transformation. So here's another example by combining several fundamental building blocks together. Okay, and this one is using the segmentation, not the deep learning segmentation thing. Also, if you are using any segment anything by Meta, you can get a quite good result. Yeah, I think segment anything can replace all the things here, but still, in this notebook, it's going to show you how to use the OpenCV ways to do segmentation. I'm not going to show you the notebook anymore today, because right now I believe that segment anything is a much better choice, and probably no downside at all. You can skip the segmentation method, but just note that there are some segmentation method exist in OpenCV library, and still they might have some ideas that can inspire you. So if you have some ideas about segmentation, and you are asking yourself or other people, why didn't people use this way to do segmentation? It seems so simple and effective. Then probably people already use it, because a lot of simple or naive, maybe not naive, but simple idea about to doing segmentation are explored in maybe 80s, 90s, or 2000s. And there are tons of different ideas and algorithms to do the segmentation. They achieve certain level of successfulness. But the modern way is segment anything too, of course. But this workshop is conducted like I think 5 years ago. So back then, I think they are still have some usefulness. But right now, the practical useness is reduced just because the segment anything model exists. But the example you see right here is not in the notebook. This is in a true work pipe to extract the images from. I think I was doing some training some generative models to generate images, to fine tune some models to do that. But I need to remove the background, and the background here is quite. I thought I need to make every character to in a more align them to a more straight to the center of the image. I do not want them to have more white space left on right or left on the right side, because originally they have a lot of padding. So I want to find out where the character is, and in some pictures they have more than one characters. I mean, in this one they have more than one characters. So I want to separate the characters so that each image have only one character. So the reason that I use that segmentation is because it is an easy one. You can see that the background is quite easy. It is white. So I use some algorithm to do that, and it can achieve quite good result already. So I don't need to use like segment anything back then, and the segment anything doesn't exist back then. But right now, if I have segment anything, probably will just ask it to do it automatically. If it doesn't work, I simply give some point of each character, and then probably I will get my result. But it still has some benefit because there are many different pictures. This is just one of the picture. So I want to do it like more automatically. But they are not that like 100 picture or 10,000 images. It's more like 10 images. So although I want them to do it in an automatic way, but still, given each character a hint point, it's not that difficult. I probably would, if I do it right now, I probably will do it in a different way. But anyway, this notebook gives you some sense of how to do the segmentation correctly. Okay, so that's probably most of the hand-on examples. So let's move on the other functionalities of OpenCV and the skimages. I'm not going to. I didn't provide the notebook, but kind of like before, we give a quick review of the functionalities it contains. So one way to find it out by yourself is to look at official website of OpenCV. It contains many different usable examples with images, result image, and videos. So I'm strongly recommend that you reading these tutorials have a sense of what it can be done. So one way is segmentation that we did before, and it works on the playing cards, different than the one that I have, definitely, but it works quite well. And one useful tools to use is a dilation and erosion. It proves to be very useful in pre-processing and a lot of different works. They are both based on simple algorithms. For the dilation, it just simply extend each image, each pixels if it is beyond some threshold, and we expand each pixels to be larger. The kernel can be different. because if you can assign it to be straight in the horizontal direction, or stretch it in the vertical direction, or maybe in both directions. It depends on your kernel. Erosion is, on the other hand, kind of like a complement or opposite operation to a dilation. It only keeps the pixels that has surrounded by certain kernel. So it can be considered like the dilation of the black pixels. If erosion on the white pixels, it kind of like the dilation of the black pixels. So by using these two operations, you can remove some gaps of your data. Or sometimes, so this is dilation, the formula of dilation, and the erosion, kind of like these two operations. So for example, like here, if you want to remove the noise small things, you can first do the dilation. So this is open to find the open point. You can first use a dilation to remove these small things. I mean erode. Erode is making things smaller. So you can erode first, then make a dilate. So if it is in a large block, or it has a lot of neighbor, positive neighbor that is in a white, then it will remain the same. But if it is in some isolated small block, small things, then it will disappear. So it will serve very well on like image cleaning, or if you are doing some segmentation things, you want to clean out your result, and you already know that this is the issues you want to handle. You have to deal with. This is a very useful tools and controllable, manageable, because you know how it works. So another thing is that if we have some small holes in our like things, like synchronization things, you can use the dilate first, then use erode. So the shape of the things you are interested in, it still remains roughly the same, but the small holes is going to be filled. So this is called the close operation, and this is called the open operation. And sometimes you want to find kind of like the boundary things. You can use dilate minus erode. So here's some example that's provided in the OpenCV tutorial to let you to explore this method, this erode and dilate things interactively. So one interesting and actually useful thing is to remove the result is to remove the horizontal lines in the musical scores. So we keep this each musical notes one by one, but we want to remove this horizontal or vertical things. You can actually use the erode and dilate, combine them in a more intelligent way to do so without using other things like more like deep learning models or other things. You can actually achieve this kind of result. This is useful for things like a lot of real world tasks, because especially for cleaning. So one task we used to do, one project we used to do is to recognize a curve that is drawing on a board. In a lot of machine, it has a curve about like the machines, like the pressure level, or like the Fallon level or temperature levels, and it will draw a curve like which is the safe region. However, the curve is read by human, and it has a grid on it, kind of like the straight line and the vertical line here. It has a grid on it. So when people take a picture of that graph, that is probably on a metal plate near the machine. First thing we should do is do the perspective transform, like what we do before, to make it more like a straightforward facing to us. And the second, we are going to use this similar method to remove the grid lines to get the curve itself. Then we can apply some recognition algorithm, simple algorithm, because we don't actually need some deep learning algorithm because it is just a curve. We are reading this curve. If this curve is plot perfectly on using matplotlib, then we can simply use an algorithm to extract information from this curve. And similarly, we can do it similarly. If we remove the grid and grid like straight and horizontal and the vertical lines, and we make the perspective transformation correctly, then we can use algorithm to do that. Also, that can be done quite practically. Like we demonstrated before, there are a lot of different ways to do edge detection. There are more modern ways like using deep learning models or more advanced method. Although still in algorithm, there are many different ways to do that. But OpenCV still provides quite a range of fundamental, classical, basic ways to do edge detection. And sometimes you will find it to be very useful. Another thing is to do the line and the circle detection. Here is a small example that I take. Try to find a lot of circle in it, and it can find the circles from these images. Not perfectly, but still it finds quite a few circles correctly. And there are some tasks that is quite amazing and interesting is to find the contour of these images. There are different meaning of what contour is. So one thing is to find like a bounding box or like a circle around each of the things. Sometimes it just need to find a convex polynomial. So there are different meaning of contours and different tools to find contours. One way to use it along with your deep learning algorithm is deep learning models is to help you to make some good visualization. So sometimes if you do segmentation of things, the shape is not so good, but if you combine with this contour overlay on it, it will seem to be quite interesting on the visualization result. So I think it's worth mentioning that OpenCV consists many tools in this category. Another interesting application is out of focus deblur filter. So there are some kind of like super resolution, but it is doing for deblur. It's based on some mathematical formula and some assumption. It can achieve certain like best result if based on certain mathematical hypotheses and from assumptions, mostly on from assumptions. So here is a result that you can expect it. Although visually, probably you still prefer the result from deep learning models because currently we have a lot of amazing models, generative image generating models like diffusion models or like game models. Especially recently, the development of diffusion and related models achieve very high fidelity. So you probably we probably won't feel very satisfied about this ripple effect on the images. But still, it's quite amazing. By simply using mathematical formula and theory, we can sort of getting things like this one. And because it uses mathematical formulas only, it will not have things like AI illusion, or it will not have hallucinations. Everything here is reliable because it is just solving some mathematical equations. However, this is sort of like a hit or miss situation. Sometimes it doesn't work that well. In this case, it works quite well because you can actually read the text on here. You can read the text. This deblur filter works quite good if it is actually blurred by the Gaussian blur filter in an ideal blur filter. But in real world, if you have a blurred images, this is probably the best thing you can get. This is probably the best result you can get. And sometimes you don't get things like readable. So if you have a low resolution or like a blurred image of a book, you probably won't get that good result like what we see right here. But sometimes it works, and I think it's worth noting. This one is for a motion deblur. So the thing here is not the only. It is for autofocus deblur, and there's also for the motion deblur. You can imagine there's some mathematical models behind these motion blur things. So by using this motion deblur, this is probably also the best thing you can expect from this function. But as you can see, at least in this result, we can see the car plate more clearly and more readable. In this one, I don't think anyone can read the result right here, but at least we can see something. And we are free from the AI hallucinations because this is based on the mathematical formula. So the result is reliable. If you are using like a diffusion model or other AIs, and you give some prompts like, okay, this is a car plate, you are going to get something really, really clear. But you probably won't rely on the result. Like if it says some numbers, plate license numbers, you probably won't trust the result to be real result that much because it will hallucinate a lot. But this one is only for mathematics. The only issue is that it doesn't work. It is sort of like a hit or miss, and the hit rate is probably not that high. And if it is miss, it is probably because fundamentally you don't have information on the blur image. So that's something we need to manage and handle. And it also can do for a high dynamic range image. Because usually camera sensor can catch the lightness in certain range perfectly, but our eyes can adjust to different levels. So sometimes our eyes can see more details in color and lightening. We can mimic these things by combining different images together, like in the in a more dark scenario and the more bright ones. Combine all these things, so this becomes a more high dynamic range image. The high dynamic range can be shortened for HDR. So if you have some HDR device or seeing some HDR image on YouTube, they are the same thing. It's just because some device can provide a more wide range of coloring or lightness, so it will have HDR capabilities. And also it can use algorithm to stitching image together, to do inpainting, to do like AR, to do the pose estimations. You can use the key point matching, key point detection, and the matching sense, like what we do for the playing card. So if we have the transformation of this side and this side and this side, we can probably estimate the pose. And it also have something else, but this is a basic idea. If we already have this, like what we're doing for the playing card, if we have a template of this side and one template of this side and this side, then we can estimate the whole 3D transformation of this object. And this can work very fast in augmented reality world. And also, every camera will have some need to be calibrated, because camera will have some warpness on the edge. It will look like, I mean, a straight line in a 3D world will ideally project to a straight line on a 2D plane. But you can observe it carefully. Sometimes the straight line, a thing that's supposed to be straight line, is going to have some curvature on your photo. Well, that is because camera is not, because we have some curved lens, and this lens is not always the ideal lens. So we will not have a perfect ideal pinhole model for our images. So sometimes we need to calibrate a camera to certain parameters in order to understand the 3D world. OpenCV provides some tools to do that. Another library is the skimage. We are listing a few functionalities that is in skimage that is interesting. Although a lot of things that we mentioned in OpenCV also exists in skimage. So we probably will skip that part. First one is a histogram matching. I'm not sure it is in OpenCV, but it is in skimage. So for example, we have a source image and a reference image. We can align the color space of the source image to the reference one to adjust each one. Kind of like the white balancing or the old photo examples we did before. But instead of stretching everything into as wide as possible, it tries to match the histogram from one picture to another one. Also, that is a histogram matching. Another thing is to making the image more sharp or more contrastive, and it not only do the global equalization. It's kind of like what we do. What we did is for global equalization and for each color channel. But sometimes if we want to see the things more clearly, we can do local equalization. For example, this one is low contrast images. So we can extend the histogram. Here is the histogram here. We can extend this histogram as large as possible. So to make the image can be seen more clearly, because we are utilizing the whole possible range of the lightness, the brightness. If for the original image, it almost everything is concentrated in a very short range of the color that is for the capability of your monitor. But we stretch it more flat from 0 to 1, then we get to use all the brightness to help us to observe, to analyze these images. However, sometimes we are more focusing on the local feature, not in the global. This one is stretch everything in the global. But sometimes we are more focusing on the photo, on the local things. So the local equalization is do pretty much the similar things, but for each pixel, it only do it for the equalization to its neighbor. So it will make a lot of more details to appear than comparing to the global equalization things. So one typical example is I'm hoping I can find it. I probably should probably OpenCV. Probably can find an example in more details. A typical example is the shadow thing. The man inside a shadow. Okay, let's see. Okay, maybe this guy is good enough. Okay, so one of the local histogram equalization method is the clay. I think CL stands for like clipping things, like, and C for clipping, and local adaptive histogram equalization. So for example, like hold on a minute. Okay, for this one, if we are doing the global contrastive things, we are going to, because the people are more dark things, probably except this highlight on this man's head, because the background is more in a bright light, and these two people are more in a toward the dark side. So if we are doing the global contrastive turning equalization things, these people are getting darker, and this one is getting brighter. Although we are kind of getting more information, but this is probably not what we want. So instead, we're doing the local things. So because these two people are on a more dark side. So for a pixel inside these people, they are only compared to their neighbors. So if they are relatively brighter than their neighbor, it will getting a relatively brighter, more brighter new values. So we're adding contrast locally. So you can see that these people is getting brighter because the face compared to maybe the bodies or her hair is more bright, so it will get a more bright value here. So we can see more details. The similar things is applied to, suppose a man is in a shadow, like a building. There's a building and there's shadow, and the man stand in a shadow, and another man is standing in the sunlight. A few people is standing in the sunlight. We probably want these people to have the same contrastness to see maybe their face features or what they are wearing. So instead of doing the global contrastive turning, we do the local things. We'll see more details on these two people. So otherwise, the dark people will become more dark, and the brighter people will become brighter. That is probably not what we wish to have. Okay. The other interesting application utility is one is active contour model, like what we do the contour things in OpenCV. There are also a lot of different tools appears in skimage, like finding contours here, finding contour. If you do the contour on this head, you will find the contour of this head. So they are still very useful too. And skeleton nice things. It seems quite amazing, and you probably think it can only do in like in deep learning things, because we are kind of finding a kind of like a control net, but in reverse. we give them a people, and we'll find the skeleton of these people. But like other computer vision, classical computer vision utilities, it is a hit or miss. Sometimes it works and sometimes it doesn't. And most of the time you need to adjust the parameters. So this one, the things it shows on the OpenCV or scikit-learn example is usually demonstrate the kind of the good cases. And a lot of different cases are not the good cases, but you can see that this is a good, what you can expect for the good cases. And it can also provide some like affine transformations and piecewise affine transformations, in like what we do for the huge head things, like doing the warp transformation. And of course, this one like the perspective transformation. It can also do the registration. Like what registration means is we have two different images that are taken from a slightly different angles, but we can align these two images together. So this is unregistered images, 3 different images that they are taken in slightly different angles, but we can align them together to become this one. So you can still see something that has color to illustrate the unalignmentness, but it is huge improvement compared to the original one. And also some impending tools. Again, we can do much better. We have much better tool to do impending by using diffusion. But if the task you are looking for is for these shapes of things that you need to do impend, we can use some algorithm to do pretty much a very good job, right? What we see here, right here. If you just need to impend a straight line or some certain small dots or small rectangles, then it can do pretty much good results. But the thing is, this one works pretty well is because you can see it is all in orange. They are pretty much in the same color. And even though there's like here is a shadow in here, they are pretty straight line, kind of like straight line. So that's why they work that well, because it is an easy case. But like I said, some people are applying some modern impending models and get even worse result. That is because you didn't use the models correctly. We can get at least this much result by using classical method. One interesting features used a lot in like early machine learning and maybe in other computer vision is the HOG, histogram of oriented gradient. So HOG. Sometimes before we have a deep learning, it is difficult to handle the images by its original pixel values. So we're using some reduced features. One way to do that is we consider the like different directions for each block, because we cannot deal with high resolution image. So we kind of deal with different blocks, and for each blocks we are dealing with the gradient of the images, like a gray images. We find a gradient of like 8 of each direction. Then we use them as a feature. So you can see this is a very straightforward representative of the feature. You get this for each direction. Maybe just four direction. But for each direction, you get the different lengths of the gradient to represent the strength of the gradient of that direction. As you can see, you can see that these features by using the the image on the right hand side. It only considers HOG features, but we can probably already see this is although we didn't get the information as much as the left one, we probably cannot recognize who she is or what she's wearing, but we can still recognize this is a person, this is a head, and this is probably a suit. We probably cannot recognize this one is a helmet and this is a spacesuit, but we can clearly see this one is a face. So these features can be used for face detection to find out where the face is. Okay, so that's, and it has very, comparing to the left one, it has a very low dimension. So this helps a lot for the early algorithm, machine learning, or maybe other algorithm to find out, to do face detection. Also, you can use some simple algorithm like blob detection to detect the blob in the image. Here are different blob detection algorithm. So sometimes when you do the using some certain method to do the defect detection, you get certain blobs and you want to find them, or maybe the defect can be considered as certain black point. Then you can use blob detection to achieve the result to a certain level, and they are more controllable. They also contain a lot of algorithms. People really put a lot of effort and research on this, so there are a lot of hidden gems, or maybe not a lot hidden, but there are a lot of gems in the studies of computer vision. So here's one thing for segmentation. You probably can imagine we can take these things as maybe like the foundation and help with other deep learning models. So just look through it. You will find a lot of useful tools. And sometimes you wish to, if you want to work a shape with the transformer, like a language model, you probably cannot give every detailed pixel of this shape, but you can probably approximate this shape with a polygon. So every coordinate probably represents like 1 or 2 tokens, and you can feed them into a large language model. Also, the scikit-learn provides these tools to approximate a shape into a polygon. Another tool that I think is useful is, and this is probably the last one, is by given a 3D forum. There's a algorithm called the marching cubes, so that we can find the surface of this 3D forum. Like other computer vision utilities, you need to adjust your parameters, and sometimes it doesn't work that well. Sometimes it works, sometimes it doesn't. But at least it already provides some algorithm already coded. You can ready to use them in your project. Okay, so that's all about today's topics. I hope you can find something useful in these very rich libraries of OpenCV and the scikit images. And maybe you can also look around in the Cornea and the Simple CV, can find or DDeep. I can also find other tools not related to computer vision.